Yeah, yeah, yeah. Oh, that's quick luck. I'm so.
So I'm going to keep it muted until you walk.
That should work. Yeah, that should work, I think.
Okay, hello everyone. Thank you for coming, and we hope that more people will be coming soon. So it's my great pleasure to introduce our next speaker, which is Octavia Camps, and she received a bachelor's in computer science and electrical engineering from the University de la República in Uruguay. And she received master's and PhD in electrical engineering from the University of Washington. And since 2006, she is a professor in electrical and computer engineering department at the Northeastern University. She is an associate editor of Computer Vision and Image Understanding Journal, CVIU, and her main interests include robust computer vision, image processing, and machine learning. Let's welcome Octavia.
If the magic happens. Great. Thank you again for the invitation. It's a pleasure to be here. I'm going to talk about research that I have been doing for the last 6 years, and then I'll focus more on something very recent that we're very excited in our lab. This work is, of course, not done just by me, but also by all my students and my collaborator, Marius Nair. So today I'm going to talk about dynamics-based invariance for video understanding, and hopefully by the end of the talk I will convince you that dynamics is something that we should be paying attention to. So let me first start talking about why invariance. We know that invariance allows us to recognize objects at different scales in different places in the images, different orientations, and so forth. So allows us to reuse information and data. If we have the model for the dog standing up, hopefully we can still recognize the dog even when it's doing a flip in the air. Invariance has been paid attention in the community from many, many years, especially geometric-based invariance. On the top, you see some representative examples, and the picture on the top left is also a good representation of how the field looked like in 1992 when I graduated. You can see all males in the group. Now, more recently, the way we put invariance in our systems is just by feeding augmented data to the network with different poses and orientations, and hopefully the network learns the invariance as it learns the models. But we typically would not ask the network to learn invariance per se. Now, that's for images, and the question is, are there invariances for video, right? We could treat these videos as a sequence of frames, and therefore we have the geometric invariant for each of the frames. But I claim that there is something deeper going on here that those geometric invariants do not capture. And to illustrate my point, let me show you the next slide. And can anybody here tell me what you see?
Like an aquarium?
that's good. The image on the left, yes, is something underwater. How about the image on the right? It's cutting edge detector, yes. Okay, let's put things in motion, okay? So on the left, it's not just underwater, but there is a creature there. And once you see it, it's hard not to see it again, but you really need to see it moving. And the one on the right, yes, is an edge candy detector output of a bunch of doggies playing in the park. And so the point is that the still image and whatever geometry we can get out of it doesn't tell the whole story, right? You need to see the motion and the correlation across time to really understand what's happening, okay? And so our research has been really trying to tap into that source of information that brings temporal ordering of the data. Now, I also want to ask you that it's not just temporal video, but really the things I'm going to be talking today, they also apply to any type of data that has a sequential ordering. So yes, frames come in order, but so do pixels in a frame and pixels on a contour. Okay, so if you have a sequence that has some ordering into it, you can apply the tools that I'm going to be describing. So how do we tap into this? So the idea is to describe this temporal correlation or this ordering correlation in a way that we can actually tap it in numerical ways and teach our algorithms to exploit it. So the building block that I'm going to be using is to represent signals, temporal signals, as the output of a linear time invariant system. Now that's the simplest case, but you can have more richer descriptors by also having switch dynamical systems, like Jessica was talking today about the snippets that she was having. So if you switch from one system to another, then you can actually have a much more complex and rich description. And you can also mix nonlinearities with the linear time system to even have even more complex things, okay? Now, once we have this as our building block, then we can use my background, and I had a master's in control theory, so nothing to do with computer vision. Then for my PhD, I switched to computer vision, and I thought I would never see control again, and here I am talking about control. A linear time invariant system can be described in many different ways. They're all equivalent ways. One way is by using a transfer function, or the state space representation, or an autoregressive model and the associated Hankel matrix. And the beauty of these models is that they do carry invariance. And so, for example, the order of the system is invariant to different viewpoints, the number of the poles and the poles of the system, the rank of the Hankel matrix, the coefficients of the autoregressive model. And sometimes we can actually do a lot of reasoning just by knowing about this invariance without having to really identify the underlying dynamics. So just a quick show that how these invariants come about. For example, for the autoregressive model, it's trivially to see that if you multiply the feature vector y by an affine matrix, you get basically the same regressor. So there is invariance there. Okay. So let me briefly, very quickly, give you a snapshot view of the things that we have been able to do with dynamic-based invariance in the past. So, for example, we can clean sequences by minimizing the rank of the Hankel matrix. So on the left, you see noisy trajectories. On the right, they had been cleaned up. This was back in 2012. We were able also to do activity recognition from different viewpoints because, again, the invariants carry from one view to the other, and we could use bag of words. That was a very popular tool back then. And we did bag of words with dynamics. And we did multi-tracking and re-identification in environments where color does not help you. So if everybody's wearing a black suit, it's difficult to distinguish one person from another. But if you pay attention how they walk, then you can actually recognize them. We also did 3D activity recognition, where our dynamics invariance actually help us defining a well-defined metric to compare different activities. And we also use it to sort chronologically a set of unsorted images. So you have images of an event, maybe taken from different people, and you want to sort them out so in time, and we could do that using dynamics. But today what I want to talk about is something we're very excited. This is work with my student Wenxian Yu, that she couldn't make it here today, and Abhishek Sharma. And we are now putting dynamics inferencing into neural networks. And in this particular work, we have done is use dynamics to predict future frames. And not only is in itself that a useful task, as we're going to see in a couple of slides, but we hope that this illustrates the power of the procedure of the encoding that we're using and can be used in other type of networks. Okay. So let me introduce you to Diane. It's a dynamical atoms-based neural network for video prediction, for frames in video prediction. And the idea here is that given a partial sequence of frames, we want to generate frames ahead of time. That can be helpful to making decisions, to anticipate what to do. It can help us understanding dynamic scenes, and it also can help us doing unsupervised vision in video. Nowadays, most people, when they have to work with temporal orderings in neural networks, they use LSTM models. Now, those models are very complicated. They're hard to understand what really they're doing, the parameters that they're learning. Same thing with GANs. GANs have become very popular, but sometimes they're hard to train, they're complex, and again, the interpretation of what the generator or the discriminator are learning sometimes is difficult to analyze. In contrast, this network is going to be very simple to train, very compact, and easy to understand what it does. So it's designed using the concepts that I just very briefly talk about, dynamic-based invariance. And as I'm going to show, it has only 160 to 100 parameters, so it's very small. The parameter has a physical meaning, so when I look at what the network learned, I understand what it had learned. And it's very efficient and accurate. Okay? And because it's differentiable, it's a piece of code of network that can be actually used as a building block on many other networks, including GANs. Okay, so the network we're going to use is this particular representation of the dynamical system. So we're going to model a temporal signal as a linear combination of the output of linear time invariant systems that are very simple. They have only one or two poles. So the representation is given by the poles being used and the coefficients used to combine these responses from the systems. Okay. So here's the architecture. So you get the input video, basically just reshape it, pass it through an encoder that has dynamic-based atoms, which creates a set of sparse features to encode the temporal signal, and that these sparse vectors can be passed back to a decoder that's basically the inverse of the decoder that was used to encode the signal, and use that decoder to recover the input, but also to propagate to the future to create new frames. Here I'm showing just one, but it can propagate up to 10 frames in the future, no problem. Okay, so this is how we do it. Let's look at, this is in the frequency domain. We have set of poles around the unit circle, and they could be stable or slightly unstable. Okay, this is the transfer function in the frequency domain, and when we go back to the temporal domain, it can be written this way. And that's important because now, if we consider a pair of conjugate poles, poles come always in conjugate pairs, the impulse response of these poles can be written, this is the real part and imaginary part for this pole, and then the real part and the imaginary part for this pole. So each of these poles is given these sequences, and now what we can do is put all of this into a dictionary where the columns are these responses, and we also add one extra column over here that has all ones to be able to model a temporal signal that's basically constant, that doesn't change. Okay, so now that we have this dictionary giving a signal, what we need to do is to pick up which atoms, which of these poles need to be used to express the signal, and we want to use as few atoms as possible. So for that, what we do, we solve a sparsity problem, right? So we find the coefficients such that the input data is as close as possible as my explanation with the atoms, but I also want to use the least number of atoms, okay? And what we're going to be doing on the network is we're going to do two things. We're going to be solving this problem, but we're also going to be learning. The model that we're going to be learning is these poles. So these poles, during learning time, they're going to move based on the training data. So once we have the encoder, the decoder is very simple. We use the same dictionary, but we extend with more rows, as many rows as we want to predict future frames, where we are extending the temporal signal of the atoms. Okay? And here you see how the atoms evolve, for example, when we were training, I think this is for Kitty, yes. And that's what I refer, but I understand what's happening, because now the parameters that the network is learning has a physical meaning, are the poles of the dynamics. Okay, so the experiments that we did experiments on the Kitty data set, but training on the Caltech data set, like as a standard in the literature, and we also did experiments with UCF 101. The important thing here to notice is that we were able to do these predictions very quickly, 43 milliseconds, and the model itself can be stored in this in a very small memory. It has only 4 kilobytes for the model. So here are some qualitative examples of the Kitty data set. Again, it was trained on Caltech, but tested on Kitty. On the left, what you see is the ground truth, and on the right, you see the predicted. And so you can see that it's fairly, at least visually appealing, accurately. There's no blurriness, and again, it's quite fast because the network is so compact. The next slide will show examples of UCF 101. Here again, we have also zoomed in the areas of detail, so you can see that the image is is as sharp or as blurry as the input was, and prediction is rather good. And again, this takes only 63 milliseconds, and it was done in a very small model. So these are only visually, but we have also numbers to back up our results. So what you see here is that in terms of the error and the quality of the images, compared to the state of the art or the naive approach of just picking the last frame, it is better or comparable. But we're doing this at 1/10 of the time that it takes, and so it's faster. Okay, so what are the advantages of Diane? So first of all, as I have emphasized a couple times, the model that we learn is very compact. Only 160 parameters that corresponds to the number of poles that I have in the system. So it's very easy to train, it converges very quickly. You know, it doesn't take weeks, it takes just minutes. It's also because we are exploiting invariance in a very explicit way. We are using the invariance of the dynamics. That means that these poles are very versatile. So we can train on Caltech, but test on Kitty. We can be reusing things. So the poles are shared across pixels, across videos, and across data sets. It adapts to the complexity of the dynamics. So the number of poles that gets active depends on how complex the dynamics is. So if it's something that requires more poles, the network is going to just pick them themselves. I don't have to tell, it's a second order model or a first order model. Again, as I said before, the poles have a physical meaning. It tells me how quickly or how fast the response is going to be for a particular pixel or a particular region on the image, so we can go back and analyze what's happening there. And it produces sharp images, as we saw in the samples, and they are actually fast to do. And because the whole thing is differentiable, even the sparse problem solution, this can be put as a building block. So the next step that we're working on right now, of course, is taking these encoded features as a summarization of the video information and pass that to other networks that do, for example, activity recognition and so forth. So the idea is that this very sparse encoding has already captured the motion in a way that's easy to use. So I know I speak way too fast.
You want?
Thanks for the nice talk. I have a question related to the Diane approach that you're suggesting, because there might be something that I have missed. So since it's for video prediction, but in the scenarios that, at least the results that you showed, it seems that given the same, a few number of frames previous to the prediction, the model, if I understood correctly, will always predict the same future events, or there is some kind of stochasticity that would allow the model to predict different futures given a set of frames.
So it's a short time prediction. So it's 10 frames at the most. And so it's predicting things, for example, if a car is going to get closer to you, it's seeing when it's going to be in front of you. But it's not, it doesn't have the stochasticity that I think you're thinking about, whether the car is going to turn, right? So I'm assuming that what I'm seeing is going to continue, yes.
Maybe I also have a question. I was wondering whether different signal, like from optical flow, would, in addition to the just RGB frames that you use, would better capture the system?
Yes and no. So what we're doing, in a sense, we're actually computing optical flow. But instead of computing optical flow the way most of us understand of it, which is the Lagrangian optical flow, where you track features, what we're doing is estimating Eulerian optical flow. So we're looking at how every pixel is evolving over time. And they're very closely related. So you could put optical flow into it, and in a sense, you will be predicting almost like acceleration, because you will be doing prediction on velocities. Okay, so you can do that, and we have played with it. Other things that we have played is, for example, not working with the RGB, but working with the frequency transformation, the FFT of the signal, or passing it through a CNN and then applying the dynamics to the feature. So as I said, this is a very simple module that you can plug it in your favorite network. And the idea is that what it does capture is the temporal evolution. So that's also why in the beginning I said, don't think just of temporal signals as being video. Anything that has an ordering, it can be applied into this.
And do you think that you would need more than 160 parameters for different scenarios?
A hyperparameter that we can play with. So far, with the data sets that we have played, it was plenty. But you could have more poles. Another thing that you can have is work different temporal scales. So right now we're doing just one temporal scale, but if you want to have more breaking even farther in the future, what you can do is work at subsampling in the time. So,
okay, let's thank the speaker again. And now, so now we are going to have oral sessions. So, yes. So our first talk is entitled "Don't Just Assume, Look and Answer: Overcoming Priors for Visual Question Answering," and Aishwarya, yes, is going to present us this work.
Hello. So, hi everyone. I am Aishwarya, and I'm going to present our work on overcoming priors for visual question answering. This is joint work with my advisor Dhruv, Batra, collaborator Devi, Parikh, and my internship mentor Kembhavi. And this was presented in the main conference on Wednesday. So this is the outline of my talk. First, I will provide a brief overview of VQA. Then I will highlight some of the problems with existing models and existing setup. And then I'll talk about a novel split of the VQA dataset and a novel model which we proposed in our CVPR paper, and then I'll conclude. So let me start with a brief overview of visual question answering, known as VQA. So what is VQA? The task is the following. Given an image and a natural language open-ended question, such as what is the mustache made of, the task for an AI system is to generate a natural language answer, such as bananas in this case. To facilitate progress in this research area, in our ICCV 2015 paper, we released a large-scale dataset consisting of hundreds of thousands of questions and about 1 million answers, and this dataset is called the VQAV1 dataset. These are some of the example questions from the dataset. Some questions are about objects, such as what is the mustache made of. Some questions are about fine-grained recognition, such as is this vegetarian pizza. Some are counting questions, such as how many slices of pizza, and some questions are about common sense, such as does this person have 20/20 vision. So VQA has received a lot of attention since then. A variety of deep neural models have been proposed for this task. And there have been several challenges on VQA till now. So my colleagues and I organized the first edition of the VQA challenge. It's CVPR 2016, and about 25 teams participated in the challenge. And then we organized the second edition of the challenge at CVPR last year, which saw about similar participation. And then we organized the third edition of the challenge this year, which saw 40 teams participating in the challenge. So there has been a lot of excitement around VQA recently. So despite this excitement, there have been some problems with the existing setup and the models, which I would like to highlight now. So a number of works, including REM NLP work, have found that these models are heavily driven by superficial correlations in the training data and lack sufficient image grounding. So let me provide you an example. In the VQAV1 dataset, the most popular answer for questions starting with what room is kitchen. And this is an example data point from the training set. The question is about the type of the room, and the correct answer is kitchen. Now at test time, the same question is asked on a different image with the correct answer being bathroom. But existing VQA models predict kitchen as the answer. So this and other analysis that we have done shows that these models tend to memorize the prior answer given the question type and lack sufficient image grounding. So the existing setup is problematic because existing datasets have IID, train, and test splits. So the priors in the training data carry over to the test set. And hence models which rely on sophisticated memorization of training data demonstrate acceptable performance on the test set. But this makes it difficult to benchmark progress because the source of improvement is not clear. Is it visual grounding or is it memorization of priors? So now I will show how the new splits that we propose disentangles these two factors. So we call this new split visual question answering under changing priors. And this is, the split is created from the existing VQA datasets, VQA-V1 and VQA-V2. So VQA-V2 was introduced by Yash Goyal and others from our lab, and it is about twice the size of the VQA-V1 and has significantly reduced biases. So this new dataset is created by reorganizing the Twain and Val splits of the existing VQA dataset in such a way that the distribution of answers given the question type is by design different in the Twaining split compared to the test split. So consider the question what sport, all the questions that start with what sport. And in the new split that we propose, tennis is the most frequent answer in the Twaining split, whereas skiing is the most frequent answer in the test split. So let me demonstrate with an example how we created the splits. So here I'm showing two question answer pairs, each from the Twain and the test split of the original dataset. So first we merge the question answer pairs from the Twain and test, and then we group these QA pairs such that the questions belonging in one group have the same question type and the same ground truth answer. So for instance, what color is the dog with the answer white, and what color is the plate with the answer white are grouped together, whereas what color is the cat with the answer black is put in a different group. And then we greedily redistribute the QA to the new Twain and test split such that the questions with the same question type and the same ground truth answer are not repeated between Twain and test. And while doing this re-splitting, we maximize the coverage of the test concepts in the Twaining split just to make sure that the models have seen those concepts individually in Twaining. So to demonstrate the difficulty of the proposed splits, we report the performance of several existing models, including the challenge winner from the VQA challenge, first round of VQA challenge, after retraining on the new splits. And then we compare their performance with those on the original VQA-V1 split, and we find that the performance of all these models drops significantly on the new splits compared to the original dataset, which demonstrates how difficult the new splits are. And the trends are similar for the VQA-CP-V2 splits. So now I'm going to talk about a novel grounded visual question answering model that we proposed in the CVPR paper. So we proposed this GVQA model where we impose inductive biases in the model to prevent the model from relying on priors in the training data. So this model explicitly disentangles the space of possible answers. So for this question, what room is this? The space of possible answers is all types of rooms. And this is disentangled from what visual concepts in the image need to be recognized to answer this question. So for this example, we need to recognize that there is a sink, there is mirror, and there is a bathtub, etc. So let me explain the model architecture in more detail. So given this image and the question, what color is the dog, we encode the image using activations from a CNN, such as VGG, and then we extract the main part of the question, which is the part that tells us which part of the image I need to focus on. So for this question, what color is the dog, the main part is dog. So I have highlighted a part of this string in red and part of this string in green. So the part of this string which is in green is the part that we are interested in extracting, and the rest is the question type that we remove from the question. So basically this extractor removes the part that has been highlighted in red, and the output is the part which is highlighted in green, and that tells us where in image we need to focus on. So this extractor is basically a simple rule that removes the question type, and the question types are provided in the dataset for the training time. For the test time, we just do a lookup over the question types. So now this encoded image and this Q main, which is the output of the extractor, is fed to a module called Visual Concept Classifier, or VCC. This VCC looks at the image and attends to the relevant part in the image, guided by Q main. And for this attention part, we use the attention mechanism from an existing model called a stacked attention network. So now the attended feature vector is then passed through multiple classifiers that predict various visual concepts, such as objects, attributes, etc. So for this particular example, the predictions would look like dog, black, two, etc. Because there are two dogs, they are black in color. So till this point, the model has looked at the dog region in the image, and it has identified various visual concepts present in that region of the image, such as dog, black, two, and so on. But the model still doesn't know what to answer. So for that, we have another branch of the model called answer cluster predictor that predicts the type of the answer, such as color, number, etc. So for this particular question, the type of the answer is color. So what this module does is takes in the question, encodes the question using an LSTM, and then the encoded question is passed through a fully connected layer, which classifies it into one of the various types. And each type essentially denotes a cluster ID, where the clustering is done over the answers from the data set. So all the color answers are clustered together, all the number answers are clustered together, and so on. So the correct output for this particular question will be color, because the question is asking about color. So now, finally, the outputs from the VCC and the ACP are fed to another module, which is called answer predictor, which combines these predictions and generates the final answer. And this answer predictor basically consists of some fully connected layers. So in this case, the correct answer is black. And I would like to mention that we have intermediate supervision for the VCC and the ACP module, where the labels were automatically extracted using some unsupervised methods and some NLP rules. So we can see that we have disentangled what to recognize part from what to say part using VCC and ACP. So the model described till now was for non-yes-no questions. For yes-no questions, the model is slightly different, because the yes-no questions do not fit nicely in the architecture described before, as they require visual verification of concepts mentioned in the question. So for instance, for the question, is the person wearing shorts, we want to verify the presence of the concept shorts in the image, and if it is present, we want to output yes, otherwise no. So the visual classification branch of the model stays the same as before. That is, the model attends to the shorts region of the image and predicts various concepts such as shorts, green, etc. But now, instead of predicting the type of the answer, we have another module called concept extractor, which for the given question extracts the concept whose visual presence needs to be verified. So for this example, it extracts the word shorts from the question. And this concept extractor uses POS, which is part of speech tagger-based rules, to extract the words from the question, and then it embeds those words using glove embedding. And then finally, similar to what we had before, we have another module which we call visual verifier that combines the predictions from the VCC and the concept extractor, and combines those vectors, passes them to a fully connected layer, and classifies it into yes versus no, depending on whether the outputs of these two modules are consistent with each other or not. So this is the full model. At test time, we have a question classifier, which is basically an LSTM plus fully connected layer to classify whether the question is yes-no question or not. And if the question is non-yes-no, the ACP part of the model is activated. And if it is yes-no, the CE part of the model is activated. So we saw that GVQA disentangles the visual recognition aspect of the model from the prediction of possible answers. It also explicitly enforces visual grounding through visual concept prediction. And it does not have a direct pathway, unlike existing VQA models, from question to answer, and hence the scope for memorizing the biases in the answers given the question type is significantly reduced. In this table, we report the overall performance of the proposed model on the VQA-CP, V1 and V2 splits, and we compare the performance with that of SAN, on top of which GVQA is built. And we can see that the performance, the new model outperforms the baseline model consistently on both the data sets by significant margin. So for this qualitative example, we can see that our model correctly predicts the answer bathroom. In order to gain insights into how this model is functioning, we can look at intermediate predictions. So for this given question, what color are the bananas, and the given image, the question classifier first classifies this as a non-yes-no question. The answer cluster predictor predicts that the answer should be a color. The visual concept classifier predicts various concepts, for example, bananas, green, many, food. And finally, the last module combines the predictions from these two modules and predicts that the answer should be green. Similarly, for this yes-no question, the question classifier says that it is a yes-no question. The concept extractor extracts the embedding of the word smiling, whose visual presence needs to be verified. The visual concept classifier predicts various visual concepts, such as smiling, woman, and finally, the last module checks that these two predictions are consistent and says that the answer should be yes. This is an example of a failure case where the question classifier correctly says that the question should be non-yes, no. The answer cluster predictor is correct in saying that the question is about color, and the VCC correctly predicts that black pant, one dirt, but the VCC is incorrect. It should predict gray, but it predicts black, and the final answer is black. So now we can look at the attention map about why VCC is predicting black and not gray, and it seems that the attention is on the pants for the person's left leg, which is correct, but it is also on the socks, which are black in color, for the person's right leg. So perhaps the black prediction coming from VCC is based on the attention on the right leg. So now we saw that GVQA outperforms SAN on the VQA-CP splits, but we wanted to check how does it compare to SAN on the original VQA splits, the VQA-V1 and the VQA-V2 datasets. So in this table, we report the performance of the GVQA model on the VQA-V1 split and compare that to the SAN's performance. And we see that GVQA underperforms SAN on the VQA-V1 dataset. But this is not surprising because these datasets have well-established heavy language priors, which models such as SAN can memorize from the training set and can exploit on the test set, whereas this model is designed not to do that. And as vision improves, grounded models like GVQA may show improved performance over models that leverage priors from training data. But it is important to note that the gain achieved by GVQA over SAN on the VQA-CP is much more than the drop in the performance compared to the same baseline model on the original VQA dataset. On VQA-V2, the drop in the performance is about 1% less than that on VQA-V1. So for yes-no question, in fact, for yes-no question, our model outperforms SAN for VQA-V2. So this shows that when priors become weaker, which is the case in the VQA-V2 dataset compared to VQA-V1, the gap between SAN and GVQA's performance decrease. Another question that we asked was, okay, so our model is better at visual grounding and the existing model is better at utilizing biases in the training data. So what happens if we combine these two? Do they have complementary strengths? So what we report here is the oracle when we combine the GVQA model with the SAN model on the original data set. And basically what we do is for every test instance, we choose the model which has higher accuracy. In this case, we can see that the oracle for both V1 and V2 dataset is much better than the SAN alone. And we also compare it with the oracle of SAN to make sure that these improvements are not just because of more number of parameters. And we can see that GVQA SAN combination is significantly better than SAN combination. So this is an oracle in which we are using the ground truth information, so it is not a method. So we finally report the ensemble of the GVQA model with SAN. And we can see that the performance is better than SAN alone, and it is also better than the ensemble of 2 SAN models trained with 2 random seeds. So this basically shows that GVQA provides complementary strengths to SAN, and those strengths are better than the strengths provided by another SAN model. Another aspect of GVQA is that it is more transparent than existing VQA models because it has interpretable intermediate outputs, which provide insights into why it is predicting what it is predicting. And this, in turn, enables a system designer to identify the causes of error, which is not easy to do in existing VQA models. So to give you an example, for the image and the question, what season is it? The correct answer here is winter. The baseline model incorrectly predicts the answer summer. So you would want to know why it is saying summer. So the best you can do is you can look at the attention map produced by this baseline model, but you will see that the attention map looks reasonable because it is focusing on the snow parts of the image. Now our model correctly predicts the answer winter, and again you would want to go back and know why it predicted winter. So first you can do is you can look at the attention map, which looks similar to SAN in that it focuses on the snow parts of the image. But you can do more. You can look at what are the intermediate visual concepts that this model is predicting. And it predicts concepts like white, skiing, winter, mountains, which look reasonable given where it is focusing on in the image. And the answer cluster predictor says that the question is asking about season, which again is reasonable. This is an example where both the model fail. So the baseline model predicts that the answer is carrot. The correct answer here is pasta, but the baseline model says that the answer is carrot. You can look at the attention map, but doesn't tell you much. Our model also predicts the answer carrot. You can look at the attention map, doesn't tell you much. But now you can look at what are the visual concepts that our model is predicting, and you can see that it indeed says pasta. It says carrot, pasta, green, and plate. But why does it predict carrot as the final answer and not pasta? Because the answer cluster predictor says that the answer should be a vegetable. And carrot is a vegetable, whereas pasta is not, so the final answer is carrot. So basically, you can boil down which part of the model is failing, and you can focus your attention on that part of the model. So it is more interpretable and helps the system designer to better understand the model. So in summary, in this talk, I talked about some of the studies that have shown that today's VQA models are driven by superficial correlations in training data and lack sufficient image grounding. And as a test for grounding in our CVPR paper, we proposed a novel split of the existing VQA dataset, which we called VQA-CP, and we show that the performance of several existing models drops by significant amount on this new split. We also proposed a novel grounded model for GVQ, which we call GVQA, and show that the model outperforms the baseline model on the new dataset, but underperforms on the original dataset because of priors. And finally, when you want to deploy a VQA system, we do need higher accuracy, and if grounding of a model is not perfect, relying on priors could be beneficial because the world indeed has priors. For example, grass is mostly green, bananas are mostly yellow. So moving forward, we can think of developing models that utilize the best of both worlds, basically visual grounding and priors, and where models know when to rely on priors and when to do visual grounding. And the dataset code and models are available here, and thank you so much for your attention, and I would be happy to take questions. Hey.
Very simple question. When you did the split, when you changed the splits and you evaluated all the different winning models for the challenge, they all showed a drop, but did the ranking hold, or was it like very different as well?
We did. I did not mention it here. For some of the models that were, we did observe change in ranking. So there were two models, SAN and neural module networks, and on the original data set, I forget which one. I think SAN was better than neural module networks, but in this data set, the other one became better. So we observed some differences in ranking.
More questions? I also have one. How easy or how hard it is to extend this model to some ambiguities, like if you can have some ambiguities in answers or in questions. Like when you had this photo with bananas, right, there could be some yellow and some green depending how ripe they are. So it might, so how easy, or is it any chance to extend it to say something more sophisticated in this case, if the answer is ambiguous? But also the question can be ambiguous, like if you have a scenery and then you ask, is it sunny or not, or warm or not, you know, there is this scene data set, and then it depends on people or the one who is actually looking at the picture. For some people it is really warm, but for some people it's not, right? So it's ambiguous as well as the question, so yeah.
Yeah, so this model is not taking into account subjectivity, and it is mainly driven by the kind of data you train on. So if in the data set it has seen mostly sunny, it will tend, so the visual concept extraction part, it will tend to predict it as sunny because that's the data it has been trained on. And for your earlier question where the answer could be green or yellow both, so again it is driven by data, what it has seen in the data.
Okay, let's thank the speaker again. Thank you so much. Thanks. So our next talk will be on the iterative refinement of densely connected representation levels for semantic segmentation. And it's going to be presented by Arsha. I hope I say it more or less correct. Yes.
Thank you for the introduction. Today, I'm going to present a new architecture for semantic segmentation that combines ResNets and DenseNets. We use this architecture to test some different operations within the network to see how it affects the refinement of the features. The task of semantic segmentation consists in assigning a semantic class to each of the pixels in the image. We would like to ideally be able to predict correctly the thin objects and underrepresented classes while still maintaining a good global picture to have especially coherent predictions. To do that, we can make use of the low-level features, such as the basic shapes or colors, and also the more abstract ones that can represent the objects themselves. It would be also important to deal with the loss of spatial resolution that some of the downsamplings introduced in the literature architectures. With this, we'll be able to make fine-grained predictions. To tackle these problems, we designed this network called Fully Convolutional Dense ResNet, or FCDRN. Later in this presentation, we will see the difference between the distinct operations to enlarge the receptive field, and also whether all the feature levels need the same amount of refinement when using these different operations. And finally, we'll report state-of-the-art results in Kembhavi dataset with at least 2 times less parameters than existing methods. As I said before, this architecture combines ResNets and DenseNets. In a sequential model, each of the layers computes a new representation. This is indicated here with the different colors. However, it is said in some recent work that ResNets might not do the same. Instead, when we stack several residual blocks, what it might do is that it is refining the input representation. This is indicated with the shades of the same color here. And this level of abstraction, it only changes when there's a transformation that changes the spatial resolution. Then we stack more residual blocks, it defines this level of abstraction, and so on. So now for our segmentation model, we would like to use these refined feature levels with increasing amount of abstraction at the end of the network. So to do that, we leverage a dense connectivity pattern of the dense nets. So in the end of the network, just before the classifier, you have access to all the refined multi-level features. Now I'm going to dive into the details of the architecture. It is composed of a downsampling and an upsampling path. There's an initial downsampling block and a final upsampling one. In the middle, we can find a densely connected block. This one is divided into smaller blocks that contain a one-by-one convolution to mix the input feature maps, and then a ResNet that refines these features. Once these features have been refined, we concatenate this output to the output of the previous block, and we apply one of the transformations that can be max pooling, dilated, started convolution, or an upsampling. Then we plug in the second block that also contains another ResNet build of residual blocks, and this ResNet also refines this more abstract level of abstraction, and we concatenate, transform, and so on. So now, to each visualization, we will get rid of the dense connections and the transformations, and we will replace these blocks by some feature maps. To test these different architecture variants, what we do is fix the architecture in 9 ResNets. The 2 first variants are sharded convolutions and max poolings. They are both downsampling operations, so the shape of the network is very similar. We have this encoder part where the downsamplings are, and then in the coder part, we can find the upsamplings. For the 3rd variant, we just use dilated convolutions, so there's no shrinking of the feature map, except in the initial downsampling block. And finally, the 2 last variants take the pre-trained models with the downsampling operations, and once we have them trained, we replace the transformations in between that are downsamplings and upsamplings, and we change it by dilated convolutions. Then we further train it, so we say that we fine-tune these architectures with dilated convolutions. And this is done because we would like to ideally have a bigger spatial resolution in the bottleneck. We evaluated these different variants in Kembhavi dataset that contains 400, 200, and 100 images for training, validation, and test, respectively. And each of these pixels can be assigned to one of 11 semantic classes. So now we compare the performance in terms of Jacquard, or intersection over union, in the validation set. If we compare poolings and sharded convolutions, we can see that the first one outperforms the sharded convolutions. And if we add the dilated convolutions, we see that there's an important drop of performance here. With this, we can say that downsampling operations outperform dilations when these networks are trained from scratch. However, when we take these downsampled versions, pooling and sharded, and we fine-tune them with the dilations, we further boost the performance. Now we take our best performing network that's composed of poolings and dilations, and we evaluate them against state-of-the-art methods. In this plot, the x-axis represents the number of parameters that the network has, and the y-axis the loss in performance in terms of Jacquard. Sorry, the Jacquard in the test set. So therefore, this plot, the methods that are in the upper left side are the best performing ones. Our method, highlighted with the red square, has more than 2 times less parameters than the FC dense net, the FC dense net 103, and we outperform the results. Also, when we further fine-tune with soft targets, we also further increase the performance. It is important to notice that unless other methods in this plot, except FC dense net, we do not pre-train on ImageNet, so we could also benefit from this pre-training. Now, if we take a look at the Jacquard per class, we can see that our method in the bottom row is quite good at detecting pedestrians, column poles, and cyclists that are the underrepresented classes and more fine-grained, while still maintaining a good performance on all the other classes. If we visually inspect the image, we can see a similar result. We see that the column poles are well recovered, and also some far pedestrians and cars. So now that we have all of our models trained, we would like to know if we need the same amount of refinement for all the transformations, or how does it behave. To analyze that, we do 2 experiments. In the first one, we drop ResNet blocks, and basically it consists of taking the first ResNet, and once the model is trained, we get rid of all the residual blocks except the first one. Then we evaluate the loss in performance, and we do the same for the second one, the third one, and so on. In the second experiment, what we do is to analyze the norms of the weights and see if all the residual blocks are used or not. As for the first experiment, in the x-axis here, we can see the number of ResNet that's being dropped, and in the y-axis, the loss of performance in negative points. We can see that for poolings and sharded convolutions, it seems that getting rid of almost all the ResNets seems to affect negatively performance, but We can see a tendency, and it's that coarser feature maps that are in the bottleneck of the network seem to need less refinement, since when we get rid of these residual blocks, we are basically getting rid of the refinement. If we get rid of this refinement and the performance doesn't drop, it means that it's not fully utilizing it. Now, if we add the dilated convolution architecture, we can see a very different pattern. If we drop 5 out of 9 ResNets, it seems that the performance is almost not affected. And the same happens with the fine-tuned architectures, with the pooling and strided that have been, that we have replaced some of the transformations in between and add dilations and furtherly trained. And you can also see that in the bottleneck, where we change some transformations by dilations, the performance drop is also smaller. All in all, this seems to indicate that dilated convolutions might not change the representation level as much as downsampling operations. This could be because with max poolings or strided convolutions, we get a homogeneous receptive field, but with dilated convolutions, this doesn't happen. So this might hinder performance. Now, as for the second experiment, we will analyze the norm of the weights. In this image here, we can see one dot per each convolution in each residual block. Each of them has a smaller norm than the previous one, indicating that there is an iterative refinement of the features. If we look at the whole picture, we can see the number of different ResNets. And we can see one specific tendency for the dilated convolutions, and is that a lot of these weights are very close to 0, are very small. And for the fine-tuned architectures, we can see the same tendency for the bottleneck, where we have dilations. So now that we did these 2 experiments, we can relate them and say that residual blocks with norm close to 0 have low impact on performance. In practice, this means that instead of fully utilizing these residual blocks, it's actually using just the identity connection. So now, would it be possible to get rid of these blocks and compress the model without losing too much performance? To do that, we remove the residual blocks whose weight norms are close to 0. And in the end, we allow a different amount of refinement per each feature level. In this plot, in the x-axis, we can see the compression rate. And in the y-axis, the loss in negative points of Jaccard. For the downsampling operations, we can get rid of 8% of the parameters. However, the loss in performance is still significant, especially for the strided convolution architecture. However, when we do the same for the fine-tuned architectures, we can see that we can get rid of twice the amount of parameters, and the amount of performance loss is lower. And finally, for the dilated convolution architecture, we can get rid of almost 40% of the parameters, and the loss in performance is less than 1%. All in all, it seems that ResNets are good regularizers because they can reduce the model capacity during training, where and when they need it. To wrap up this presentation, we highlighted the potential of FCDRN, achieving state-of-the-art results in Kembhavi dataset with at least 2 times less parameters than other methods, and without pre-training on ImageNet. We analyzed the different downsampling operations or dilated convolutions that we can use, and we showed that ResNets are good regularizers since they seem to reduce the capacity when they need it. The coarser representations need less refinement, and that pooling generalizes better. And dilated convolution seems to be beneficial when they are fine-tuning an architecture with downsamplings, and also it helps to compress the model. I cannot finish this presentation without thanking the audience for their attention, and here there is the code available in GitHub. Thank you.
Questions?
Hi, I just have a quick explanation. Maybe I missed it. So you mentioned that you have a version of your model where you use soft targets for training. Could you explain what those soft targets are?
Sure. So soft targets basically means that once we have the one-hot encoding, meaning that in each pixel we have 11 positions saying if one of these classes is present or not. If it's present, it's 1, and if not, it's 0. With soft targets, what we do is that when it's 0, so there's no class present in this pixel, we enforce it to be 0.01. And when we are certain that the object is there, so we have a 1, we turn it down a bit and we put 0.9 instead. So this helps when you have underrepresented classes in your data set.
Maybe just a very practical question. How do you manage all of these experiments? That sounded really like really a lot of work, and maybe some practical notes for, a PhD students and master students that might do a lot of experiments as well. Like, how did you, some tips how to do this? This is really great.
So I trained these models on PyTorch, and a couple of advices that I would give is first try to do incremental changes, so you know for sure the changes in your performance, where they are coming from, and also try to optimize your code as much as you can, because otherwise if you end up doing a lot of experiments, you're going to take a lot more time than you need.
Thank you. Thank you. Let's thank our speaker again. Our next speaker is Carol Reiley, and because unfortunately she couldn't manage to make it here, so we're going to make a live call, and I'm going to try to set up it now very quickly, so just a minute, please. Hello. Just a second, I'm turning you on a big screen.
I have a few we didn't get to test, but it's okay if they don't play either.
And now, can you see?
Do you want me just to share the screen real quick?
Yes, please.
Share screen. Okay, share. Okay.
So I will make a short introduction and then we will start. So Carol has been at the forefront of robotics and AI for over 15 years and was the youngest member on the IEEE Robotics and Automation Board. She did her graduate work at Johns Hopkins University as an NSF fellow researching on how humans and robots interact. Most recently, she co-founded and was the president of a self-driving car startup, drive.ai. She was selected by Forbes as one of the 20 incredible women advancing AI research. She holds over 6 patents, over a dozen of publications, was the first female engineer on the cover of Make magazine, and now she's starting a new startup. So let's welcome Carol.
Great. Hi there. Okay, I feel a little bit of an echo, but I'll go ahead and start. So thank you so much for the invitation to give this keynote, and I apologize for not being able to be there in person to attend this fantastic, empowering workshop. I wanted to thank all the organizers for all the behind-the-scenes hard work I know that they did, as well as the corporate sponsors. And I'm honored to say about my experience with computer vision and robotics. I actually modified my talk today to share more about my personal journey since I'm not able to join the interactive panel later on today. So as mentioned, my name is Carol Reiley. I'm a computer scientist, a roboticist, and an entrepreneur. My mission in life is to save the world one robot at a time, no matter how grand that sounds. And I do that through building and leading tech companies that help humanity at scale. I'm interested in robotics and the idea of using robots as tools to enhance human performance and also alleviate us from doing the tedious, time-consuming everyday tasks. What I've really learned about working in robotics and AI is that it's taught me what it means to be human. And that means pushing the boundaries and realizing what our strengths are, as well as our limitations. I spent my career thinking about how do we design empathetic technology that's built for human-robot interaction and explore the ways that we influence each other for the better. But this also leads us to figure out that our biases as humans can lead to building dangerous products, which I'll talk about further on. I live out in Silicon Valley, where I am today, and I'm building my 3rd startup. I started my journey in robotics 18 years ago as a freshman at Santa Clara University, building underwater robots made out of PVC tubes, picking up objects at the bottom of a college swimming pool, and those progressed onto deep sea ocean dives. I then had the fortune of working on many different kinds of applications, mostly in regulated fields, such as building satellite systems at Lockheed Martin, people tracking for surveillance at GE Research, surgical robotics at Intuitive Surgical, transportation at drive.ai, and now on a new startup. But while these applications and domain expertise required are wildly different, which is really exciting, they're also similar in what drives me. And that is to really help people solve a problem more efficiently and at scale. And when I was growing up, I wanted to be a doctor, and I volunteered at the local hospital for 4 years, where I watched these doctors tirelessly saving one life at a time. And I was introduced to the pacemaker, which was built by engineers, which can impact millions of people at once. So off I went to study computer science, and I fell in love with robotics because of a research fellowship that required me to do research. So innovation and great products happen at the intersectionality of seemingly different things. And that can sometimes lead to what is perceived as a disconnect. And there's a disconnect between how academics and startups are perceived. One group of people are interested in discovering fundamental truths in the universe and contributing to cutting-edge research and sharing those breakthroughs with the community. And the other is about building business models, growing multinational corporations, generating revenue, and understanding customer behaviors. But both of these schools of thoughts really help push a field forward. And I'm really pleased to see that the speed in which computer vision is progressing, and there's a real blending of these two. Yet sometimes it's this natural tension between two schools of thought that provide the perspective that's necessary to build better tools and services. That includes academics versus industry, big companies versus startups, high costs, software engineers versus DIY hackers and makers. So I was really fortunate to do my graduate work at Johns Hopkins, which really intertwined industry versus academia. And we had a corporate collaboration with Intuitive Surgical, a company based in Sunnyvale, California. So I'm going to walk you guys through the history of surgery. Thousands of years ago, the image that you generally have of surgery is using a scalpel, making an incision, and possibly opening up the chest cavity by breaking the sternum to access the heart. Now, several decades ago, this was minimally invasive or laparoscopic surgery was invented. where now you operate through chopstick-like instruments, which contain a tiny camera and allow the surgeon to see inside the abdomen using a high-resolution camera. Instead of these long incisions, you have small 5 to 8 millimeter incisions, which is great for a patient. You're able to have less blood loss, you don't have a large scar, and you have faster recovery times. Now, what's bad about minimally invasive surgery is that it's really hard for a surgeon. They have broken hand-eye coordination, they can't see anything that's going on, they have no wrist motion, and it requires extra time to get this specialized training. So, at the late 1990s was the invention of robotic surgery. So here's a screenshot of the Da Vinci surgical system. It's a $2 million teleoperated robot where the surgeon sits on one side of the room and operates, and the patient and the robotic arms are on the other side of the room. And it's great for both. It has all the benefits of minimally invasive surgery that you saw earlier, but it's actually easier for a surgeon. They now have superhuman capabilities. There's hand tremor reduction, so their shaky hands are filtered out. They have motion scaling, so they can pick up something very small or also zoom up their motion. They also have 3D vision. It's very intuitive to use. But one of the key drawbacks to the Da Vinci system is that there's a lack of force feedback, or what we call haptic feedback. And that was what my master's thesis was on. I was studying the effects of force feedback in robotic surgery. And the reason why you can't just add haptic feedback on the Da Vinci tools is for a number of reasons. They're thrown away every 12 times because of these highly calibrated instruments with fine motion. They also have to go through sterilization after each use. And if you add in sensitive sensors, they don't make it through the high heat of sterilization. So what we decided to do was add these very low-cost sensors, which cost less than 50 cents, and add them on the tools so that the surgeon is able to visually see their force displayed through graphical overlays. So while they're still not able to feel anything, they can actually see something. So I'll show you a quick video here of what this would look like. We use computer vision to track the tool tips, and the circles change like the traffic light from green to yellow to red, indicating how much force. And this simple overlay showed statistical significance for novice surgeons, and they performed much better and didn't break sutures and used less force overall. But it didn't make a difference for expert robotic surgeons. That made me very curious, and I ended up picking for my thesis topic for my PhD on how surgeons learn. And it became a question of how are experts taught, what constituted an expert. It made me realize how much bias there was in surgical training and how it varied from hospital to hospital and across different countries. And there was really no way to standardize it. And this would be a place where AI could fit in. So we asked the question, is there techniques that we can borrow from speech recognition to apply it to motion recognition and evaluate someone's skill level? So could you grade a surgeon and tell the difference between skill versus style? So we're able to create this language of surgery that was used for a common, across different tasks. And we found that it was tremendously difficult, and there was so much bias in people's motions of skill versus style. So now, while I was in grad school, I spent a little less than a year out at Stanford when my PhD advisor had a sabbatical in the AI lab. And this was right after Junior had won the DARPA Urban Challenge. This was back in 2008. And while I was out there, I got to see startups firsthand, as well as this blending of academia and when people had an idea and how to bring it out into a startup. And it was interesting because both academics and startups are about testing a hypothesis or a question that you have that might be different than what would be the norm. And there was some insight into a user behavior that you had a hunch could become something bigger. While I was out there, I learned that 1.2 million people die every year from car crashes, and 94% of that was human error. And this is the leading cause of death for young adults. So if I wanted to save lives, this was probably one of the most impactful ways that I could do so. It was a global problem, and it was getting worse. And people have become more and more distracted, and I think humans are just naturally bad drivers when they don't pay attention. So, while this was intriguing, it wasn't until I saw the self-driving car as the first robot that people were going to interact with, and it was this robot in the wild, that the idea really intrigued me. This was going to be the first mass-scale robotic system, and there were key questions on how do you optimize and redesign a car if it was made with computer vision instead of human vision. For instance, you could get rid of all the side view mirrors and rear view mirrors. There's also the way of introducing this into the public that was going to be accepted. That was really interesting on the human-robot interaction component. And on top of that, was the tech ready? And it wasn't until 2015 that I started drive.ai. Because of the breakthrough in deep learning, it felt like the time was right, and this was with the team out of the Stanford AI lab. And it seemed so fundamental of a shift, and that we would have a lead and be able to create something that was a deep learning first company from the ground up. But we realized that this was a very challenging problem, and it compounded all of the issues of a startup all together at once. So it became a question that we had to ask ourselves: is AI ready to create a product that was so impactful in terms of life or death? So in 2015, we started the company, which I was president of, and then I'm a current board member and advisor. And there were really two different lenses and big problems that we saw. The first was, is the tech ready? And that was the question of what types of sensors do we use? What vehicle platform should we use? And what algorithms do we pick? And you'll see here, we rely heavily on simulation as well as real world experience. The second question we had was, sorry, we've got these loud videos. The second question we had was on user acceptance. And this is not only the user that might opt in for the self-driving car ride, but the general population around this car. So as this self-driving car is now on the roads, how would it interact with the pedestrians on the street or the other vehicles, the motorcyclists, the bicyclists, and how do we get to build a product that people actually love and use and trust? And I think that's one of the biggest unanswered questions today. And both of those, the tech as well as the user acceptance, are two heavy problems that face self-driving cars. I just wanted to share this picture because I really love it. This is a picture from the Industrial Revolution when we had the first disruption in transportation. This is a snapshot of New York City in 1900s. The first shows one automobile in a world full of horse and carriages. And we see 13 years later that same spot and how most of the vehicles on the road are all cars now that the Model T has had mass adoption. As well as you'll notice the infrastructure of the cities have changed. What once was dirt roads have now transported into concrete streets. And I think the AI revolution is bringing about this next wave of transportation disruption. In 2015, over 253 million cars in the US are filled with vehicles, and 95% of households own at least one car. Now, I hope it takes 13 years or less for this next AI revolution as we move from traditional cars into self-driven cars. I'm going to show a quick video. I don't know if there's a way to turn down the video volume, so I might have to talk over this, but here's a video that we released over a year ago of our vehicles driving at nighttime. To date, I'm just going to play it for a few seconds. So to date, we've secured over $77 million in funding, led by our Series B VC NEA, which is the largest VC fund in the world. We partnered with automotive and ride-hailing companies. We have over 130 employees. We've launched in Texas and California and are working on our international deployment. So, we've accomplished a lot in the last 3 years, but as an exec of the company, it was really important to me that inclusion, just like safety, was baked in from day number one of the company. I think too often, diversity and inclusion is an afterthought that's kind of slapped on after the core development is done. And we always get a lot of pushback in regulated companies on safety, because that's something that innovative R&D engineers don't like to hear. But if you don't have those things in parallel, it becomes a very painful redesign, and there's a high level of technical debt that you'll have to pay as you go through version after version. So it was really important to us early on to have discussions of diversity and inclusion. I did a huge push to hire a VP of HR early, and I think that's important for any startup, as well as had the team go through unconscious bias training. So, with AI becoming the new electricity, and it's moving so quickly that it's going to disrupt and power almost every industry, it's important that we move fast but remain very thoughtful. I think it's no secret that self-driving cars as well as AI is the next great space race. There's a worldwide investment in AI, which doubled from 2016 to 2017 to $12.5 billion in funding, half of which went to China. And I wanted to highlight the fact that, I think one important thing for female-led companies is that since I had led fundraising, the end result actually was that we have a high percentage of females on our board. So in Silicon Valley, where only 7% of the VCs are female, we have 3 out of 10 and observers, which are female, and that's much better than the typical Silicon Valley company. So I'm often asked, what really scares me about AI? Is it the loss of jobs and the displacement of the people? Is it killer robots? But what really scares me about AI today is the same thing that really scares me about humans, which are bias, cultural insensitivity, and ethics. And this is going to be problematic as we move forward, since AI can be used everywhere. It not only powers voice assistants and drives our cars, it's also being used for HR departments as they sift through resumes, decides who gets parole, and examines medical images. And as it gets more widespread and important, these AI missteps and abuses become more dangerous. If we don't get this right, sexism, racism, and other biases are going to be literally encoded into our lives and trained on incorrect data that continues to leave women and people of color, disabled, and other marginalized groups out of decision-making. Now, we've seen this happen before. I'm in the automotive space. It's another male-dominated area. Crash test dummies were used for safety testing, and women were 47% more likely to be seriously hurt in an accident, and pregnant women weren't even considered. And it wasn't even until 2011 when female crash test dummies were being used. So this is still a problem that's at the forefront, which I hope AI can help expose the limitations and weaknesses of. So AI is making a lot of headlines recently, and I'm glad to see that this is becoming a problem that people are talking about and being aware of and have acknowledged. And we've seen lots of errors from big companies in terms of face recognition and skin tone products and NLP products. So here's a recent study from MIT that showed less than an error rate on products of less than 1% on white males, but up to 34% error rate on darker skinned females. Things like the Apple Watch were not able to detect a heart rate on darker skinned people or people with tattoos on their wrists. We also see errors in terms of products for NLP where tonality and pitch aren't recognized for children or women. And for an industry like self-driving cars, that's not going to be good enough. There's high expectations and pressure from the public. Everyone is watching, and there's a really low tolerance for forgiveness. One accident from any company will set the entire industry back. And Drive AI is a startup, and we can't afford to accidentally hit a darker skinned female or child in the middle of the night. And so those are things that keep us up at night and that we think heavily about. So artificial intelligence is really going to bring out the best and the worst in humans. It not only mirrors us, but really amplifies our inherent biases in a raw and filtered way. So I've been exploring how to address the fact that these data algorithms and systems have biases embedded within them, reflecting the designer's explicit or implicit choices, historical biases, or social priorities. What it's going to do in the next few years is expose us for our weaknesses as humans and make us confront fundamental questions about ourselves. And this process of designing AI is critical because as engineers and designers make progress in the field, we will unknowingly pass along our biases, just like a teacher would to their students. So ultimately, we must push AI not only to improve on our limitations in human intelligence, but also on our limitations in human empathy. So thank you so much. I'm happy to answer any questions with the remaining time I have. Feel free to shoot me a question or email later if you want. My Twitter handle and email are up on the top. Thank you.
Let's thank the speaker. Thank you very much. Very nice talk. And is anyone wants to ask a question? I will just bring a mic to the audience.
Okay.
We have a very shy audience today.
All right, sure.
No, but I think maybe just because we would have like a very nice panel discussion later on, and maybe just like a last, like maybe if you have like one sentence or like your word to our participants of the workshop, what would you like to tell us or to say?
Yeah, I have 5 pieces of advice for any young professional or student. I think it's really important not to burn out. So, when I was in grad school, I tried to optimize to stay awake as much as possible. So I slept in small, shorter shifts, and it completely ruined my social interactions. But I was able to I think sleep in 2-hour blocks like a med student to get to maximize work in my 20s. But I think it's extremely important to get sleep and to take breaks. So that's definitely one piece of advice. I think I get about 7 hours of sleep a day now, and it's just more productive. The second is it's extremely important to exercise and drink water. So I know this sounds like your mom, but it really does help get your energy up and happiness level up. The third is to spend time with friends and family, doing things that you love. So I think it's important to not only spend time with people like other graduate students in School of Thought, but people outside of your comfort zone and normal social circles. So joining groups is a fantastic way with people with common interests and people who went to different schools so that there's more of a diversity of thought or different people with different economic backgrounds. I think it's important. My 4th piece of advice is sponsorship. So try to find someone that is a sponsor for you. And there's a difference between sponsorship and mentorship. And mentorship means that, someone who you kind of get coffee with once in a while and check in on you. And a sponsor is someone who really will pull you through that pipeline and help you with your career. So it's important to look for sponsors. And they could be men or women. And both are very helpful and have different perspectives. And the very last one is to, no matter what you choose in your career, to always optimize for learning. So really try to take a path that you will learn the most, even if it means failing. And I ask that you guys are all bold and try to do something different. And don't be afraid to fail publicly and embarrassingly because you'll learn a lot. So I think that's really about taking a path that helps you optimize for learning. Thank you.
Thank you very much. Thank you. Finally, before the break, we would still have 2 talks, 2 presentations. And the first one is gradient-free policy architecture, gradient-free policy architecture search and adaptation by Saina.
All right. Hi, everyone. My name is Saina Ibrahimi from UC Berkeley. Today, I'll be presenting our work on gradient-free policy architecture search and adaptation. It's a joint work with me, Anya, and Trevor Durrell at UC Berkeley. This has been a paper published at Coral Conference on Robot Learning. So most of the previous work done in developing end-to-end vision-based driving models are based on imitation learning, or so-called behavioral cloning. What it means is that mapping raw pixels to some sort of actuations that you can steer the car with. The first work in this direction dates back to Alvin project in late 80s, where they used a shallow, fully connected network to train 1,200 images on a 100 megaflop CPU. Then it was DARPA autonomous vehicle called Dave back in 2004, which was a remote controller call that uses a CNN and trained on images to drive through narrow path and avoiding obstacles on the road. Inspired by the two previous work of Dave and Alvin, NVIDIA company picked up the work in more than a decade later and started a project called it Dave 2 with a lot of more data and a lot of more computational power. They showed that they were able to successfully drive a car that was trained on images labeled with steering angles. Later in 2016, some folks in our lab at UC Berkeley collected a large data set of dashcam video camera of nearly 3 million images, and they used an architecture of a fully convolutional network combined with LSTM, and they were able to predict ego motion. So one might ask this question that what is the best architecture to use? Seems like everyone is using a different architecture. And what should we do if we want to do the same? Should we fine-tune one of the off-the-shelf models, or should we come up with our own model? We all know that either way requires hyperparameter tuning, which is very much time-consuming, and trial and error and performing all of them and finding which one works best for us is also expensive, especially when you're dealing with very large data sets, such as the case in self-driving cars. So what is the solution? Is there a way to automate this whole architecture design process? Or is there a way that we can define a specific cost that we can afford in terms of the number of parameters that we can work with and design an architecture with that number of parameters? Is there a way that we can specify a goal of performance that we want to achieve with the network that we want to design? So the answer to all these questions is yes, and we're going to show it in our work how we do so. But before doing that, let's discuss one more question, which is also another caveat with the behavioral clone models. So this is the question that, do they really generalize well? Is a behaviorally cloned model able to avoid crashes of any kind? The answer is, of course, not. Imitationally learned models are very much well known for not being able to generalize when there is a significant shift from the source domain to target domain. I have few examples here to show that such a model, at least in our experience, which I will talk about in a bit, would fail at. For example, this is a case that the light is green and a pedestrian is passing by the street. A behaviorally cloned model learns traffic signs very well, so it knows it has to continue when the light is green and it has to stop when the light is red. But here's a confusing case for it. The light is green, but there is a pedestrian, so it gets confused. There's also another case here. There's a car that is trying to pass the intersection, but suddenly the light turns red. So what a human driver does is just, we pass. We don't block the intersection. But a behaviorally cloned model knows the light is red, it has to stop, so it causes trouble. Or in general, any kinds of unseen incidents during training, such as animals, such as crazy pedestrians, anything that jumps on the road, or anything that has been rarely happening during training would cause problem at test time. So how should we adapt to a new domain that we haven't seen before? We think the key solution to this problem is using a reward-based approach. But one might say that it crashes so many times to begin with, and this video shows that. If you've ever worked with any RL algorithm, you know how many crashes you need to make until you learn a little bit. So we suggest that do not start from random initialization because it's not sample efficient. Start from a behaviorally cloned model so that your model will be sample efficient and you will make least number of crashes possible, causing a safe learning algorithm. So the way we tackle this problem is in 2 steps. We automated the architecture search process by defining it as an optimization problem where we set what we want to achieve by the neural network that we are going to design in terms of both performance and computational cost to do the imitation learning to mimic the expert policy. And the second step, we adapt this policy to the target domain using rewards, resulting in a safe learning method that we will discuss. For both these steps, we use a gradient-free optimization algorithm. So let's first see how the architecture search will be done. Here's how prior work at Google Brain designed an architecture. They defined every layer with their hyperparameters. For instance, a convolutional layer can be defined using its filter width, height, stride height, width, etc. And they used a recurrent neural network to predict these hyperparameters in a sequential manner. So this recurrent neural network will serve as a controller or a parent network or a meta learner, has different names, to train a child network. Each time the parent makes a prediction, the child network will be trained on demonstrations and achieves an evaluation metric. That will be used as a reward signal back to the controller so it can update itself. Our contribution in this part is that we showed we can use a gradient-free approach to do so, to train the parent instead of a gradient-based approach such as reinforcement learning, which has been used before. So the algorithm works as follows. We have a parameterized reward function, and we perturb the parameters in random directions. We evaluate twice in a feed-forward manner and use finite difference to estimate the gradients. So by gradient-free, we mean that we estimate the gradients without analytically compute them. The reward-based function is set such that we optimize both cost and performance, meaning that the architecture won't grow unless you achieve the desired improvement that you have asked for. So there are 2 benefits for using a gradient-free approach as opposed to a gradient-based one. First is faster convergence because you're not doing backprop. And the second one is no vanishing gradient issue, which is a very common problem in training recurrent neural networks. We used Grand Theft Auto game for the whole project. We collected more than 2 million images labeled with steering angle, brake, and throttle. And these are some samples from the source and target domain that we had. They're equally difficult, and they have distinct weather and lighting conditions. So here we show our results for architecture search for behaviorally cloning on GTA. Our baseline was NVIDIA structure that had 250K parameters. So we first set our goal to stay below this number of parameters and get a better performance. And we were able to design a small architecture that does so. And then we removed this goal and we said, we don't care about the cost, just give us an architecture that beats the 2. And we were able to design a larger architecture with a lot more parameters, but better performance. Here is a better visualization of the loss gained in these 3 scenarios. There are also more comparison between us and the baseline in our paper, which is cited below. So here we show how it looks like inside the GTA game when you have a behaviorally cloned model. Left one is the baseline, and the right video is our large design network. The bar plot also shows the loss gained by our model, green, versus the baseline in red. So what you see here, they are semi-reasonable, but there are some incidents that they're struggling with, such as maintaining the lane line keeping or maintaining the required throttle that you need on a slopey road. So the takeaway from here is that, as you saw earlier from some other few examples, that a behaviorally cloned model is not the ultimate solution for driving end-to-end. So far we have covered the architecture search, and now we want to adapt the learn policy on demonstrations to the target domain using rewards. So we have a binary reward based on lane line keeping and crash avoidance. We receive 1 if we comply and 0 otherwise. So we have a policy learned on demonstration in source domain with large architecture that we designed, and now we give rewards in 3 different scenarios. from left to right in the videos, we give rewards on source domain, second target domain, and third both domains. Here is a sample video of how the model behaves, but it's easier to compare based on some quantities. So we compare the loss. The bar plot here shows the loss gain in each scenario. Intuitively, you think that the more model gets exposed to different domains in terms of rewards, the more it learns. And that's exactly the case, indicated by the lowest loss value achieved when we gave reward on both target and source domains. Note that the 4 orders of magnitude drop in the loss when we switch from behavioral cloning only to following up by reward-based optimization. So we were able to reach 100% average reward after 53 hours of training, and we were able to play in the game for 90 minutes without any mistake until I ended the game. And we also see here how our approach on learning from demonstrations would help with making a safer learning algorithm. And by safer, we mean less number of crashes that you make until you train. And the bar plot shows the number of crashes for with and without demonstrations learned model. And also the left graph shows the number of episodes that it takes for a model to converge to an average reward for our model and the baseline. So as you see, it takes forever for a randomly initialized model to learn something versus a behaviorally cloned model. So final remarks, we showed that we performed architecture search to mimic the expert policy. We optimized both performance and the computational cost, and we were able to outperform the baseline. We also showed how to adapt the learn policy by rewards to a new domain which hasn't seen before. And we showed that combining imitation learning with reward-based approach can achieve remarkably better results, and with gradient-free optimization results in faster convergence as well as starting with less number of crashes, which is safe learning. Thank you, and you can watch more videos or read about the project on my website. Thanks, and I would love to take any questions. Use this. Questions? No, it doesn't.
How's battery moving?
I have a battery. Well, I can. Any questions?
There you go.
Oh. Now it's time to have some questions. No? I was wondering, at one point you said, I mean, it's a well-known problem that if there is some event happen that it was not in training data, right, then the system can't do it, right? So can you get some inspirations from the zero-shot learning or few-shot learnings models to tackle these problems or not? You know, the zero-shot learning is like when you don't have a training, like when you don't have training data, but you still are capable to predict at test time. So at least some inspirations. I'm not saying, you know, you can apply it, obviously not, but yeah, just some ideas on that.
Yeah, definitely. You can use zero-shot learning, any sort of zero-shot learning algorithm that can help with, but in an online learning setting, it would be probably harder to do so. And the goal is to learn more general concepts rather than just the specific scene that has been seen before. So if you show lots of pink elephants during training on the street, your car probably learns that and will never hit a pink elephant. But it doesn't distinguish it from a, I don't know, red tiger on the road. But during reward and making lots of crashes, it learns not to hit any obstacle, regardless of how it looks like in terms of the features. So it's more about an action and state scenario that it needs to understand the concepts rather than specific features associated with any any sample that it has seen during the training. So it's more about state and actions.
Yes,
Yeah.
thank you. Sure. Okay, let's thank the speaker again. Thanks. And I think we have our last speaker for today before the break and the panel. And so the presentation would be on joint event detection and description in continuous video streams by Shu, Lee, Ramanishka, and Sigal and Sayenko. And the presenter is Hoi Chan.
Hello everyone, this is Huijuan Xu, come from Boston University. Today I'm going to present our work about joint event detection and description in continuous video stream. So this is a joint work with Bo Yang, Vasily, Leon, and Kate. So first, this video captioning task, it requires you are giving a long untrimmed video, so you are required to detect interesting events inside and provide a caption description for it. Previous method takes C3D network as well as an LSTM to encode input video. Then the LSTM hidden state is used to predict a set of proposals. After get this set of proposals, the same LSTM hidden state is used to predict, is used to represent this set of proposals. So this will cause inaccurate proposal feature representation, since for the set of proposals, you are using the same LSTM hidden state to represent them. And also, the proposal module and captioning module are trained separately. So the captioning nodes won't affect the proposal module to help localize the proposal boundaries more accurately. Also, in previous method, only visual context is considered. However, if we look at this example, it contains a series of actions to finish the task of wet lifting. However, this series of actions are context with each other, both visually and in language. Thus, we propose a hierarchical captioning model to model both the visual context and the language context. So this is our proposed model called JDNet. It's an abbreviation of Joint Event Detection and Description in Video Streams. It contains more accurate proposal features. And the proposal module and captioning module are jointly trained to benefit each other. Also, we build a hierarchical captioning model to take both the visual context and language context into consideration. So first, for the video feature encoding in JDNet, we take the 3D convolutional neural layers to encode a long sequence of video frames. It can encode up to 768 frames. After we got the feature encoding for the whole input video, we are going to use the segment proposal network to predict a set of proposals. So our segment proposal network consists of two 3x3 convolutional layers, followed by a max spatial pooling. So the max spatial pooling is used to get rid of the spatial dimension. So after max spatial pooling, we have one feature vector at each temporal location. Then the feature vector at each temporal location is used to predict a set of proposals with respect to anchor segments. So here, two loss is applied here. applied here. The first is the proposal binary classification loss. The second is the temporal coordinate regression loss. So after we got the predicted proposals, we need to extract proposal features for these proposals. Here we use a 3D segment of interest pooling. It's actually a 3D extension of the 2D IOR pooling used in object detection. So the basic idea is we divide the input features into fixed number of bins, and then we sample one value from each bin. By 3D SOI pooling, we are extracting proposal features uniquely for each proposal. Compared to previous method, they use the same LSTM hidden state as feature representation for a set of proposals. Thus, our proposal feature representation is more accurate. After we got the proposal feature representation, we need to decode the proposal feature into captions. Here we take the hierarchical captioning model to take both the visual context and language context into consideration. So the hierarchical captioning model used here is composed of a controller LSTM and a captioner LSTM. The controller LSTM is used to encode the video context as well as the previous sentence history information into controller LSTM. The hidden state in the controller LSTM is used as a context vector in the captioner LSTM. So in captioner LSTM, it uses the context vector from controller LSTM as well as each proposal feature representation to decode each word in the sentence one by one. So in our hierarchical captioning model, we take both visual and language context into consideration. Next, I'm going to introduce the training loss we used in JDNet. So the total loss is composed of two parts. The first is the loss. First part is the loss used in a special proposal network. The second part contains the loss used to train the caption part. So the loss in the special proposal network contains a binary proposal classification loss as well as a smooth L1 loss for coordinate regression. And the caption loss contains the sum of the log likelihood of predicting each word. One thing we need to mention is that our proposal module and captioning module are jointly trained in an end-to-end fashion. So these laws are trained together in the end-to-end model. So we evaluate our JDNet model in two large-scale data sets. The first is the ActiveNet caption data set. It contains around 20K videos with 25 train val test split. So here is an example from that data set. Each video contains several segment annotation with paired captions. So we evaluated JDNet for both proposal metrics and captioning metrics. For proposal evaluation, we take the average recall at TRU threshold 0.8 and average recall at TRU threshold between 0.5 and 0.95 for top 1,000 proposals. So our first separate trained special proposal network outperformed previous proposal models based on a DIP model as well as its multi-scale extension. After joint training, the proposal results improve compared to a separate trained special proposal network. For captioning evaluation, we compute the blue, Meteor, Cider, and Roger L metric at TRU threshold 0.3, 0.5, 0.7, and 0.9 for top 1,000 proposals. So the table shows the result. So first, Our first JetNet separate trained model improved the meeting score by 2.55% compared to previous best model, with other metrics being slightly lower. So after joint training, the joint trained JetNet improved all the metrics compared to the separate trained JetNet. So this indicates the benefits of end-to-end joint training for both proposal and captioning module. Then with the incorporation of visual and language context in the hierarchical captioning module, all the metrics further improve. We also evaluate our model on the TACUS multi-level dataset. So it's a dataset based on cooking videos. It contains 143 training videos and 42 test videos. So this is one example from that dataset. It's recorded in the kitchen environment. Compared with the activated caption dataset, TACUS multi-level dataset contains more intensive annotation, and the captions in this dataset becomes shorter compared to activated dataset. We also evaluated proposal and captioning metrics on this dataset. First, for the proposal evaluation, compared to after joint training, the average recall at TRU threshold 0.8 maintains almost the same, but for average recall at TRU threshold between 0.5 and 0.95, it increases. For the captioning evaluation, we come to the same conclusion. First, after joint training, all the metrics improved compared to separate training. And furthermore, with the context incorporated, all the metrics further improved. So this is one demo from the activated captions dataset. A person is seen walking down a gym with a large group of people on the side. The man then jumps into the air, begins to jump around. The man then jumps off the mat and walks away. This is a demo from the TACUS multi-level dataset. The person enters the kitchen, opened a drawer, took a cutting board and a knife out of the drawer. Place the knife, open the refrigerator. Took a cucumber from the refrigerator. It's actually a leek, so it's a misprediction for the object, but for cucumber and leek, visually they are both green. Yeah, I find that in this dataset, most action description in the sentence is correct, but when it involves some small objects, sometimes it mispredict the object. So this demo is relatively long, so I will just stop here. So that's all my talk. Thank you. Any questions?
Questions? Okay, I have one. I was wondering, actually, if I understood correctly, that the actions, even though we can see the video as the video goes, then you predict a lot of actions, right? But you don't really take into account the sequence of actions that you can, instead of just learning one at a time action, you can learn a bit more complicated thing, like what actions are followed by which actions. You know, like when you peel, I don't know, orange, then you throw the peel, and this is typical. So you can learn like longer sequences of actions. Did you think about it, or if I understood correctly, you just do a single one?
Yeah, so you are talking about the context information with each other. So for one action, it composed several small actions sequence. So this can be context with each other. So I actually try to take this into consideration in building the model, in the hierarchical captioning module. But this kind of context information, it can be, it's slightly useful, but it's not so obviously, because it is a context with each other, but when people collect this data set, they didn't intentionally design this kind of context. So when you propose some context model, you can still benefit somehow from it, but the result improvement with this kind of context modeling is not so obviously. I think most probably because the dataset collection is not intentionally with this kind of context into consideration.
Okay, sounds good. Anything else? Okay, let's thank our speaker again.
Thank you. Thank you.
We will have a break now until 4:30, and then please come back for our panel discussion. That is going to be really, really interesting, so don't miss it. See you. Yes, and if you have anonymous questions, please send us on the form. The link is on our website, and you can also tweet. Is it also the Twitter? And also Twitter hashtag, so we can just directly get them and ask our panel. Thanks.